So this is the second part of section 4.7, and this problem that we're going to look at is a lot of times referred to as the lifeguard problem. It's actually a little variation of the lifeguard problem, but the lifeguard problem actually has a lot of examples in nature also. Normally in class, I pass around a couple of handouts that talk about a couple of these from nature. One of them is from Tim Pennings, who is a math professor at Hope College. He did a math seminar here a few years back where he brought his dog with him, and he wrote a paper that was published, and it was titled "Do Dogs Know Calculus?" And what he noticed was that if he would take his dog along Lake Michigan, so here's the lake, these are the waves, and over here is the beach, and he would be standing here with his dog, and he would throw the ball out into the water. Well, his dog was one of those dogs with really short legs, and he could run a lot faster along the beach than he could swim. So the idea is this: if they are standing here, and he throws the ball into the water and it lands right here, so the dog, if you wanted to get there the fastest, it wouldn't be fastest for the dog just to swim all the way, even though that's the shortest distance. It turns out it would be fastest for the dog to run along the beach to a certain spot and then jump in and swim. So you can see it's not the shortest distance, but it would be the shortest time because he can run much faster than he can swim. So this is an example of the lifeguard problem, and this professor just noticed that it seemed like every time he would throw the ball in the water, it seemed like the dog was going about where he should to get to the ball in the quickest time. So finally he conducted some experiments. He had a friend of his out there helping him, and they did this repeatedly and found out that the dog did seem to be jumping in at about the right time. Since we're online right now, I'm going to send an email with a link to that paper so you can read it. It's an easy read. It's kind of interesting. And there's another one too that there was an experiment done with ants, and ants also seem to know about the right spot to go in here to get to the ball in the shortest time. Of course, with ants, it was a food source, and they had, I think it was like higher carpet here and then smoother surface here. So the ants would eventually figure out, again, the shortest time to get to the food source. And this has been documented in other areas also. I've also seen an example where it was using people, where they had this. I saw an example with kindergarten kids, and these were not really controlled all that well, but we had this surface here was a parking lot which was plowed, and then this out here was really deep snow. So the kids could run along this surface really quickly, and they would go real slow here. So the example that I saw, very similar to this problem with the dog, where a teacher stood here with the kindergarten student and would throw the ball out to here and ask the student to get there the fastest. And people seem to have lost this ability because most of the students just went flying through the snow. So maybe it was just fun of the snow. But anyway, I have seen other experiments that were more controlled that show that people do still tend to have this ability. So varying results there, I guess. And it may even be settled now. This was a few years ago when I was looking into this more. But for our problem, what we're going to do is just look at this example where we've got this swimmer at a point 500 meters from the closest point on a straight shoreline. So first, let's get rid of some of this, and so you can have a clear picture here. sure there's a way to do this without wasting time on the video, but I couldn't figure it out very quickly. It was not cooperating, so okay, here we go. So we've got this swimmer who is 500 points from the closest point on a straight shoreline. So I'm just going to draw this. Here is our shoreline. This swimmer is 500 meters out here. So it's 500 meters from the point on this shoreline. So here is 500 meters. And so this is the water out here. Uh-oh. You know what that is? That's a shark. Hopefully he's a fast swimmer. And he needs to reach the cottage that is located 1,800 meters downshore from the closest point. So 1,800 meters downshore from this closest point. So we got to go down here 1,800 meters. So around, let's do this. Here is the swimmer. Let's say this is about 1,800 meters down here. And the question is this. If he swims at 4 meters a second, so if he's in the water, right, this is all the water here, he swims at 4 meters a second and then walks at 6 meters a second. So how far from the cottage should he come ashore to arrive at the cottage in the shortest time? So the question is this, should he just swim here and then run across? Should he swim all the way across? Or should he swim part of the way and then run the rest of the way? Well, he swims slower than he walks. So probably what's going to happen is we're going to have something like this, where he will swim part of the way. So this is the path he'll take. He'll swim part of the way and then get to shore and run the rest of the way. So if you ever need to convert from meters per second to miles per hour, which you will a lot of times in physics, I'm going to show you a really easy way to do it. If you have meters per second and you multiply by the square root of 5, you'll get an approximation to miles per hour, which is usually accurate to within a couple of decimal places, because the square root of 5 is pretty close to the conversion factor you need to go from meters per second to miles per hour. So if you have meters per second, just multiply by the square root of 5 and you'll get a pretty close approximation to miles per hour. Now if you do that here, you're going to see that these numbers are way off. So I think originally I had different units on here, because if you figure out 4 meters per second, this guy is super fast at swimming, because 4 meters per second, that's about just under 9 miles per hour. Now, Michael Phelps swims at about half of that speed. So this guy is an all-star athlete. And he's also pretty fast just at walking. He walks at 6 meters per second. Well, that's 13.4 miles per hour. So just walking, he would get under a 5-minute mile, which is pretty fast. So this guy's a stellar athlete, and maybe he'll be okay even with the shark. So just out of curiosity, though, to see how fast people are compared to other animals, the fastest human sprinters, they hit top speed. They can hold it for about 20 meters. Top speed of a human is about 28 miles per hour. This is just extra stuff we don't need. For a human, about 28 miles per hour. Now, if you compare that to other animals, a greyhound dog, how fast? About 45 miles per hour. What about a horse? A horse, about 55. These are top speeds. And of course, these numbers will vary somewhat by source, but depending on where you look. But they're going to be close to this. A cheetah, everybody knows this one, about 70 miles per hour. Domestic cat, about 30 miles per hour. What about an elephant? Here's a surprising one. Elephants run about 65 miles per hour. Can you believe it? Now, hopefully you don't believe that. I completely made that one up. I don't know how fast elephants are, but I know they don't run 65 miles per hour. They're probably surprisingly fast, though. So anyway, this is our picture. So we want to know, where should this person who's here, where should this person come ashore if they want to make it here in the fastest time? So remember, we're minimizing time, not distance. If we're minimizing distance, we just go straight line, but we're minimizing time. So just to keep in mind what's happening here, this person, while this person is swimming, their speed is 4 meters per second. When they're on the ground running, walking, it's 6 meters per second. So we've basically got this situation. Let me move this up a little bit here. So we've got 1,800 meters here. And we could think of this as being a right angle. And we want to know basically, where's this point? Where is that point right there? So we've got this point here on shore. So the way we can do this problem is we need to minimize the time. There's going to be time spent swimming and time spent running. So you guys have seen many times from a long time ago, we had distance equals rate times time, right? We want to solve for time, so we're going to divide each side of this equation by r, and we'll get time equals distance over rate. So we're going to need this formula, and we need to figure out the time swimming and the time running. We're going to have to add the time swimming to the time running and try to minimize this time by moving this dot along this line. Right, so the two extreme cases would be you swim 500 meters, run 1,800 meters. That's one extreme case. The other case is you swim all the way. That'd be the other extreme case. So we want to figure out the time. So we need distance over rate. Well, we have the rates, but we need the distances. So to set up the distance, we need to think of like this is two different points. So what we can do is I'm going to call this distance here x. If I call that x, and this other distance has to be 1,800 minus x, right? Because if we add these two together, we have to get 1,800 meters. So 1,800 minus x plus x is 1,800. And there's a reason I didn't put x here. I could have put x here and 1,800 minus x here. The only reason I didn't is because to find this distance, I'm going to need the Pythagorean theorem. So I'm either going to have to square x or square 1,800 minus x. The algebra is simpler if I put an x here. But we'll get exactly the same answer if you switch these around, right? It doesn't matter how I label this as long as they add up to 1,800. So I purposely put the x here because I know that we're going to have Pythagorean theorem when it comes to the length of this. So time equals distance over rate. For the running portion, we've got the distance and we've got the rate. We've got both of them. For the swimming portion, we've got the rate, but we need this distance. And this distance comes in when we use the Pythagorean theorem with these two sides, so that this distance, the distance, this red line swimming, is going to be the square root of a squared plus b squared, which is basically 500 squared plus x squared under the radical. So once we have that set up, now we can come up with our formula. We want to minimize time. So the time, I'm just going to put x here. Time is a function of x. And it's going to be distance over rate swimming. The distance is 500 squared plus x squared under the radical. The rate is 4 meters per second. So that's going to be 500 squared plus x squared under the radical, divided by the rate, which is 4, plus we've got the other time also, the time spent running. So we've got the time swimming, we have to add the time running. And the time running is also going to be distance over rate. So that distance will be 1,800 minus x over 6. And you could notice we do have a constraint here. X has to be less than 1800, right? X has to be less than 1800. It won't really come into play other than maybe I'll just make a note of it anyway. Those will be our two extreme cases. So X has to be between 0 and 1800. So if X equals 0, that would be X is 0. That's the extreme case where we swim all the way and then run all the way. When X is 1800, so this dot goes all the way to here, that would be the extreme case where we swim all the way. So we're going to find out if there's an X in between here. So we've got time, a couple things to note. Number one, we want to minimize time, right? We want to minimize this. We want to minimize time. The other thing that's kind of nice is when you look right here, we've only got one variable, just X. So we don't have to eliminate one of the variables. We've only got one variable. So we are ready to go right here. But before we do this, because we're going to have to take the derivative to find the critical numbers, so I'm just going to rewrite this in a way that'll make it easier to take the derivative. I'm going to write it like this. And this just makes taking the derivative easier. So we need to take the derivative of this because the derivative, when we set the derivative equal to 0 and solve, we'll get the critical numbers. And those critical numbers are where the max or min could occur. So that's what we need to find. So at this point, you should probably press pause, find the derivative, set it equal to 0, and then come back and see if we agree. So, okay, to find the derivative, first I need a little more room here. And let's go ahead and find t prime of x. So we've got the power rule, 1/2 times 1/4. So we go 1/2 this to the 1/2 minus 1, right? So you get 1/2 this to the minus 1/2. And this is not plain old x, so then we need to take the derivative of the inside by the chain rule. So t prime of x will give us 1/8 500 squared plus x squared to the minus 1/2. Then by the chain rule times 2x, right? Because the chain rule says take the derivative of this. Well, this is just a number, right? You don't do the power rule here because 500 squared is just a number. So the derivative of any number is 0. The derivative of x squared is 2x. So then when you go and take the derivative of this, well, this one has an easier derivative than it looks. 1/6 just goes along for the ride, and the derivative of this thing is just -1, right? So the derivative of this whole thing is just -1/6, right? Derivative of this, -1. The 1/6 goes along for the ride, so we get -1/6. So if we clean this up a little bit, we have, let's see, we would have 2x, you have 8, and if I rewrite this thing to make it a positive 1/2, we could put it underneath a 1. And I'm just going to, instead of using rational expressions, I'm going to use a radical. So we would get 500 squared plus x squared minus 1/6. And let's just clean this up because these are both even. That goes once, that goes 4 times. So you end up with, let's see, x over 4 times the square root of 500 squared plus x squared minus 1/6. And what we want to do is set this equal to 0. So because we want to find the critical numbers, we set this equal to 0. And then I'm going to do something that we'll see repeatedly in these kind of problems. We're going to have a situation like this. Now to solve this equation, I'm going to set up a proportion. So I'm going to add 1/6 to each side. And this technique will work on a lot of these optimization problems. So you'll kind of get very familiar with this right here, because once we have a proportion then we can get rid of these fractions by taking the cross products. So if we do this, we're going to get 4 times the square root of all this equals 6x. And then I'm just going to divide each side by 4 just to clean this up a little bit. And we will get 500 squared plus x squared equals 6 over 4x, or 3/2 x. So then to solve this equation, we need to get at this x, and it's under a radical. So we are going to have to square both sides here. So we square both sides, square this side, square this side. Remember, we also have to square the 3/2. It's an easy mistake to make, is just to square the x, but we need to square this too. So when we square both sides, we end up with 500 squared plus x squared equals 9/4 x squared. So if you think of this, I'm just going to subtract x squared from each side, but I'm going to think of it as 4 over 4 x squared, 4/4 x squared. Then when I subtract it from 9/4 x squared, I get 5/4 x squared. So we get 500 squared equals 5/4 x squared. So then x squared, I'm going to multiply each side by 4/5. Get 4/5 times 500 squared. And we don't want x squared, we want x, so now I take the square root. I don't have to think about two solutions here, because x for our application is a distance, so it needs to be positive. And if you figure this one out, you'll get x equals 200,000. Actually, we'll get the square root of that. I need to do one more step here. So x is equal to the square root of that. So x equals about 447 meters. So again, we need to answer the question. That's not the answer. That's x equals. And your answer to your boss when he or she is asking you to solve a problem is never going to be x equals 447 meters. So to answer the question, if we look back at that graph, 447, what we've got is that this thing here is 447 meters. But the question is, basically, what's this distance, right? This is the question. What's this distance? How far from the cottage should he come ashore to arrive in the shortest time? So we have to find this, we go 1,800 minus x, and the answer would be 1,353 meters. Now really, we need to check that. That's our critical number. Our critical number is 447, but that gives us an answer of 1,353. But to really answer the question, we really should check the endpoints. Now, a lot of times, almost all the time actually, the endpoints are going to be the two extreme cases, which will not be the ones we're looking for. But just to see how this works, if we wanted to find the time, want to find that minimum time, we need to go back to our original formula, which is right here. Right, this is the function we're trying to minimize. Now I need to plug my x value of 447 in here and here to find that minimum time. So we answered the question already. The question was 1,353 meters. At least that's what we think it is. So to verify, to make really sure, we can try this. We can try plugging in t of 0, right? Because we said originally that the two extreme cases were x equals 0 or x equals 1,800. So we should plug these in. So we plug in the two endpoints and we get these two. And then we plug in the critical number. So to plug in the critical number, we plug in our 447. And when you do this, you're going to see that this is about 425 seconds, 467 seconds, and this is about 393 seconds. So this one is the fastest way to do it. So he should arrive 1,353 meters from the cottage. So that's the answer, 1,353 meters from the cottage. And I mentioned that we checked these 2 points. The extreme points will very, very rarely in an applied problem give us what we're looking for. We can see that these 2 take more time than if we use this one. So there's one more problem on our worksheet here, and then we'll do a couple of them. We'll probably finish this one on this video, and then we'll put a couple of them from the book that are good ones, and I'll probably make another video for those. So we've got, in this case, we've got the cylindrical can with a closed bottom and closed top. It's going to be constructed at a volume of 1 gallon, which is 231 cubic inches. You can see how awesome the system we use is. This came from, this gallon was defined by Queen Anne in Great Britain in 1706. And just like all of our English system measurements, it's just like a random number. So we're stuck using it though, unfortunately. So we've got 1 gallon, which is 231 cubic inches. And then they've got material for the bottom and the top, which is 6 cents, right? $0.06 is the same as 6 cents per square inch. The sides is a little cheaper material, right? 3 cents or $0.03 per square inch. And we want to find the dimensions of the can that minimize the total cost. So first what I'm going to do is just draw a picture of this. So we've got this can. Goes like this, and we've got the cost of the sides of the can, and this is $3.03 per square inch, and the tops and the bottom has a different cost. As you know, cans typically do have a different material on the top and the bottom. And this cost is going to be 6 cents, or 6 cents or $0.06 per square inch for the tops and the bottom. So we want to find the dimensions of the can that minimize the total cost. So the way we do this, the way we do all of these kind of problems, and these are the kind that I typically ask you about, because if you ever get paid to solve these problems that involve mathematical functions, most of the time you're trying to minimize the cost. Sometimes you're trying to minimize a distance or maybe the amount of material or time, but a lot of times your concentration will be on the cost. So these are the kind of problems I typically will be more inclined to ask on tests or quizzes. And the way we can do this is we want to break this up into pieces. So we've got a top and a bottom, and we've got this side piece. So think of it like this. What if we took this can and we cut it right down the side? Well, couldn't you think of it as we've got this top piece and this bottom piece that are circles? And then if we cut this can, let's say we take the top off, take the bottom off, so we've got this cylinder. If we cut the cylinder here, then couldn't we just flatten this thing out, just flatten it out, and we'd have a rectangle? So if we did that, we would basically have this. We would have this rectangle that would be the side of the can, right? That's the side of the can, the rectangle. Then we would have a top and a bottom, so we'd have 2 of these, right? So we basically have the side, or like the side of the can would be the rectangle, then we have the top and the bottom, which would be like this. And when you work on these kind of problems, it's best to just split them up into pieces and then put the pieces together. We need to think of the cost. So the cost is in terms of the area. So when we figure out the cost of this thing, we can think of, well, we've got to find the cost of this. Cost equals, well, we've got to figure out the cost of this side piece and the cost of the top and the bottom. So to think of the cost of this side piece, we know that the side is $0.03 per square inch. So we need to figure out, well, how many square inches are in here? Well, we've got a couple of dimensions here. We've got the height. This is some height. Whatever the height of the can is, we'll call that h. Now this distance here, so this is a rectangle, so we have like length times width or base times height or however you want to think of it. We need to find this length. But that length really is just the circumference of the circle, right? So circumference of a circle, we know the circumference of a circle. We've got a formula for that from algebra class. Circumference is 2 pi r. That's the circumference of the circle. So if we want to find the area of this thing, the area formula is just length times width, base times height, however you want to call it, but it's going to be this times that. So I'm just going to write the area in here. So the area of this is going to be 2 pi r h, right? That's the area of this piece right here. It's just 2 pi r times h. And then we've got the top and the bottom piece. Well, these are circles, right? We know the formula for the area of a circle. The area of a circle is just pi r squared. So this area is going to be pi r squared. But remember, we've got two of these because we've got the top and the bottom. So we've got two of these areas. So to think about this cost, we can now figure the cost of this. Here's the area of this, and whatever the area is, we're going to multiply it by 0.03. All right, so the cost is going to be the 0.03, the cost, times the area, 2 pi RH, plus we need to add the cost of this. Well, first there's two of those, right? There's two of them. So whatever the cost for one of them is, we double it. So I'm going to put a 2 there because there's two of them. And then the cost of the top and the bottom is $0.06 per square inch. So the cost, you put 0.06. And then we just have to think of the area. Well, the area we know is pi r squared. So now we multiply this by pi r squared. So we can clean this up a little bit, and we'll get 0.06 pi RH plus 0.12 pi r squared. So we've got our cost function here, and we want to minimize this. So minimize this. Here's a pro tip. If anybody ever asks you later on to work with a cost function, you're going to want to minimize that. Don't come back with a way to maximize it, or it could be your last project. When it's a cost function, we want to minimize it. Now you might notice looking at this, you might look at it and feel a little bit sad. Do you know why you would feel sad looking at this? We've got R and we've got H. We've got this cost function in terms of two variables. That makes us sad. So we want to somehow figure out a way to get this in terms of one variable. We want to eliminate either the R or the H. Pi is a constant, so we don't care about that. So we need to know something else about this. And here's where, if you look up the original problem, it says that the volume has to be 231 cubic inches. So we're going to have to use that now. So we can use that right here. We can say, well, we know that the volume is 231 cubic inches, and the volume formula for a cylinder, just think of it, for a cylinder, think of, we know the area, and now we need to add a dimension of height. That's all you need. So if you have any kind of geometric object where you just move it straight up from the ground, the volume of that thing will be the area times the height. So the volume of a cylinder is the area of the bottom, which is pi r squared, times the height of this, which is just h. So the volume of the cylinder is going to be pi r squared h, and we know also it's got to be 231 cubic inches. So we can use this part of this equation right here to solve either for r or for h. Looking at this, it'd be much easier to solve for h. So I'm just going to solve for h, and then I can just plug it in right here in this one spot. So to solve for h, we say h is equal to 231 over pi r squared. So then what we can do is take this h right here and plug it in right there. So then we will have the cost is equal to 0.06 pi r times h, which is 231 over pi r squared, plus 0.12 pi r squared. And then we can just clean this up, and we'll eliminate one of these variables. So you can see that definitely the pi will cancel. One of these r's will go, and we just get 0.06 times 231. And if you use your calculator here, we will get the cost is equal to, this would be 13.86 over r plus 0.12 pi r squared. And now we've got what we want. We've got our cost function in terms of one variable, one independent variable, just r, and that makes us happy. So we've got our cost function. I'll make a note of this real quick. Here's our cost function. So if we want to minimize the cost, we're going to have to use this function. We need to find a critical value and find a critical number, and then we're going to plug it in here when we're done to figure out the cost. So we're going to need this later. But to find the critical number, we need to find c prime. We need to find the derivative, right? Because if we find the derivative, set it equal to 0, and that will give us our critical numbers. And then we can plug in our critical numbers and our endpoints. And I'm going to just kind of ignore the endpoints. The endpoints are like weird areas where r could be 0, or r could be the maximum value it could be, but the minimums are not going to occur there, or the maximums. So they're going to occur in applied problems at the critical numbers. So let's find those critical numbers. So in other words, let's take the derivative and set it equal to 0. So I'm going to rewrite this a little bit differently. I'm going to write it as 13.86 r to the minus 1 plus 0.12 pi r squared. So then c prime is going to be negative 13.86 r to the negative 2 plus 0.24 pi r, right? Just taking the derivative. And then this one, we want to write this as a fraction, which we can do if we just, basically want to write this as a positive power. We don't want r to the negative 2. We want r to the 2. And all we're going to do is use this formula from algebra. X to the negative n is 1 over x to the n. So we'll use that right here. So this is really 1 over r squared, right? This is 1 over r squared. So if we rewrite it that way, we get c prime is equal to negative 13.86 over r squared plus 0.24 pi r. And we want to set this equal to 0. And then we're going to get that familiar format from before where I mentioned we can make this be a fraction equal to a fraction. To get rid of this negative, I'm going to just add this to each side of this equation. So if we do that, we end up with 0.24 pi r equals 13.86 over r squared. And just to make it be a proportion, I'm going to put this over 1. And that allows us to just take these cross products, and we'll do this repeatedly in these optimization problems. So we end up getting 0.2, whoops, I want this, let's undo that a second. So we end up getting 0.24 pi r cubed equals 13.86. So that means that r cubed is 13.86 divided by 0.24 pi. And right here, a lot of things go wrong all the time. We have to be careful with this. So we've got r cubed, we want r. Here's the easy mistake to make. Take the square root of both sides. We don't want the square root of both sides. You want the cubed root. The easiest way to take the cubed root is just to raise each side to the 1/3 power. It's usually just easier on the calculator. But that's not the biggest problem. The biggest problem is this denominator. We have to make sure if you just plug in 13.86 divided by 0.24 pi, it's going to divide these two, then multiply that answer by pi. So we have to be careful here. This happens constantly. This has to be in parentheses. Or you just have to, multiply them first. But we have to be careful with the order of operations. And if you do this correctly, if this is done correctly, you should get r equals about 2.63917. Okay, so that gets us here. So this is our critical number. Now here's where more problems come up. If we're going to find the cost, when we talk about cost, you always, you typically go to 2 decimal places, right? To cents, go to dollars to the second decimal place. So here's what I see all the time. To find the cost, people will plug this into the equation or plug this into the equation. You don't want to round too quickly like this. These are all bad, both bad. So remember, we don't cover significant digits in this class. Those will be covered in physics and in chemistry. So what I can say in general is when you're using a number in a calculation, like this will be, we're going to have to use this in a calculation, save a lot of decimal places, and then just round your final answer. Because if I just plug in 2.6, I have no hope of getting this accurate to the penny. It's going to be definitely wrong. So plug in a lot of decimal places, round your final answer, and you will tweak this concept in physics and chemistry. So, all right, so we've got our critical number. So they want us to find the dimensions of the can, diameter and height. So if this is the radius, then we can find the height because we have this formula from earlier that said the height equals 231 over pi r squared. So remember that formula from earlier? We used it to eliminate a variable. Well, now we can use it to find the height. So we take this number and plug it in here for r. Again, don't just plug in 3 or 2.6. Plug in extra decimal places and round at the end. And if you do that, if you plug in this number for the r here, you'll get a height of approximately 10.56 inches. So the diameter, because they want the diameter too, well, we know the diameter is just 2 times the radius, right? Diameter is 2 times the radius. So if we double r, we get about 5.28 inches. And then they want to determine the minimum cost. Well, that's where we're going to take this number and plug it back into our original cost function. So remember the original cost function, which is this one right here. So we take this number for r, and we're going to plug it back in here. Again, use a lot of decimal places and round at the end. And if you do that, you'll get a minimum cost of $7.88. But I'm going to show you a really easy way to do this, to plug this in, because a lot of times what will happen is students will get this right. They have this value right, then they get the wrong answer. So a really easy way to do this, it's hard to show on this video, but when you do this calculation and you get this you get this number here, right when you get that number, look on the far left column of your calculator for a sign that says STO with a little, let me rewrite this. It looks like STO. It means stores in. There's a button here. It's a button above the on button. Well, when you get this answer, just hit this button and then hit your X button. Hit the button that says X, comma, T, comma, theta, comma, N. Hit this button next. Okay, that's a button towards the top, just below the mode button. So you get this answer, hit stores in here, and it will store it in X. Then it's really easy to figure out the cost without making any mistakes. You'll have a whole bunch of decimal places in X, and then you just type in your calculator 13.86 divided by X plus 0.12 pi X squared, and you'll get the answer. So this technique eliminates errors really easily. Just whenever you get this answer, hit stores in X, and then type this formula, but wherever you see an R, put an X. And then order of operations works out nicely, and you just get your answer. So it's just something that can eliminate some errors. So remember with this section, this is a challenging section. I'm going to end this video here because it's getting a little bit long. And we put another video together with some of them from the book that are good problems that I want to make sure we're solid on. But this section takes practice, so make sure you practice. Put in your time on this one, and I will talk to you guys soon.